Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the technical report titled CDE, Curiosity-Driven Exploration for Efficient Reinforcement Learning in Large Language Models. Are you ready to explore the intersection of curiosity, reinforcement learning, and large language models?
Absolutely. This paper is quite fascinating, especially since it addresses some of the core challenges in reinforcement learning for LLMs. To start, can you give us a high-level overview of what the paper is about?
Of course. The paper introduces a framework called Curiosity-Driven Exploration, or CDE, which aims to improve the efficiency of reinforcement learning in large language models, particularly in reasoning tasks. The key idea is to use the model's own sense of curiosity to guide exploration during training.
That's interesting. So instead of relying solely on external rewards or traditional exploration strategies, the model leverages its own uncertainty or curiosity to decide what to explore next. Is that correct?
Exactly. The authors formalize curiosity using two main signals, one from the actor, which is the model generating responses, and one from the critic, which evaluates those responses. For the actor, they use perplexity as a measure of curiosity, and for the critic, they use the variance of value estimates from a multi-head architecture.
Perplexity as a curiosity signal is quite clever. It essentially means that if the model is surprised by its own output, it considers that output more novel and worth exploring. But how does the critic's variance come into play?
The critic's variance reflects uncertainty in value estimation. If the critic's heads disagree a lot about the value of a particular response, it suggests that the model hasn't explored that region of the solution space enough. This variance is then used as an exploration bonus, encouraging the model to visit those underexplored areas.
That makes sense. Before we get deeper into the CDE framework, can we talk about the context? What are the main challenges in reinforcement learning for LLMs that this paper is trying to address?
Great question. The main challenges are premature convergence and entropy collapse. In RL for LLMs, models often exploit known high-reward strategies too early, failing to explore alternative reasoning paths. This leads to a lack of diversity in responses and can cause the model to get stuck in suboptimal solutions.
I see. So traditional exploration strategies like entropy bonuses or epsilon greedy policies don't work well in these high-dimensional, complex environments. Is that why the authors propose curiosity-driven exploration?
Yes, exactly. The paper points out that count-based exploration methods, which work well in simpler RL settings, are computationally expensive and not expressive enough for the long, complex reasoning chains in LLMs. The CDE framework is designed to be both efficient and scalable for these scenarios.
Let's break down the CDE framework. You mentioned two curiosity signals, actor-wise and critic-wise. Can you explain how the actor's curiosity is computed and used during training?
Certainly. The actor's curiosity is measured by the perplexity of its generated response. Perplexity is the negative average log probability of the generated tokens. If a response has high perplexity, it means the model finds it surprising or novel. This value is then used as a bonus added to the original reward, but with adaptive clipping to prevent the model from favoring novelty over correctness.
That's a smart safeguard, so the curiosity bonus is capped relative to the original reward, ensuring that the model doesn't just chase high perplexity, low-quality responses. What about the critic's curiosity?
For the critic, the authors use a multi-head architecture, where each head is trained on a different subset of the data. The standard deviation across these heads' value estimates for a given response is used as the curiosity signal. High variance indicates uncertainty and under-exploration, so the model is encouraged to explore those areas more.
That's a neat way to approximate uncertainty. Does the paper provide any theoretical justification for these choices?
Yes, it does. The authors present two theorems. The first shows that the perplexity-based bonus penalizes overconfident errors and promotes diversity among correct responses. The second theorem connects the critic-wise bonus to classical count-based exploration bonuses in linear MDPs, grounding their approach in established RL theory.
That's reassuring. Now let's talk about the experiments. What datasets and models did the authors use to evaluate CDE?
The experiments were conducted on 4 challenging mathematical reasoning benchmarks: METAS, AMC23, AIME24, and AIME25. The models were based on Qwen 3-4B base, and the training was done using the Vural framework. The authors compared CDE against standard PPO and GRPO algorithms.
And what were the main findings? Did CDE outperform the baselines?
Yes, CDE consistently outperformed the baselines. For example, adding the PPL bonus to GRPO yielded an average improvement of about 2.4 points across datasets, with even larger gains on some benchmarks. Multi-head PPO also showed consistent improvements over vanilla PPO, especially as the number of heads increased.
That's impressive. Did the authors analyze why CDE works better? For instance, how does the bonus weight decay schedule affect performance?
They did. The paper shows that decaying the bonus weight over time is crucial. Strong exploration in the early phase, followed by a shift to exploitation, yields the best results. The staircase decay schedule, which maintains high exploration initially and then drops the bonus abruptly, was found to be most effective.
That aligns with the intuition that you want to explore broadly at first, then focus on exploiting what you've learned. Did the authors also look at entropy dynamics during training?
Yes, they did. The PPL bonus helps prevent entropy collapse, maintaining higher policy entropy during training and thus supporting better exploration. When the bonus weight is not decayed, the model fails to converge, highlighting the importance of a proper decay schedule.
What about calibration? Did CDE improve the model's confidence calibration?
Absolutely. The authors observed a phenomenon they call calibration collapse in naive GRPO training, where the model's confidence becomes decoupled from correctness. With the PPL bonus, this separation is maintained, leading to better calibration. This is important for interpretability and for inference time strategies that rely on model confidence.
That's a valuable insight. Now let's discuss the multi-head critic in more detail. How does the number of heads and the subsample fraction affect performance?
The experiments show that increasing the number of heads generally improves performance, but the gains plateau after a certain point, typically around 4 heads. The subsample fraction, which controls how much data each head sees, also affects performance, but the model is robust to different settings.
That's good to know. It means the approach is not overly sensitive to these hyperparameters. Did the authors provide any analysis of the critic's exploration bonus dynamics?
Yes, they tracked the average value of the critic's exploration bonus during training. It decreases over time as the model revisits similar trajectories more often, indicating that the model is covering the state action space more thoroughly. They also found that the critic's heads show more disagreement on out-of-domain data, which aligns with the intuition that uncertainty is higher in less familiar regions.
That's a strong empirical validation of the approach. Now let's step back and look at the broader context. How does CDE relate to other exploration strategies in RL and LLM training?
CDE builds on the idea of intrinsic motivation, which has been explored in RL through count-based and prediction-based bonuses. However, previous methods often require complex representations or additional modules. CDE, by contrast, uses intrinsic curiosity signals from the actor and critic, requiring only minimal modifications to the training framework.
That's a significant advantage in terms of simplicity and scalability. Are there any limitations or open questions that the authors mention?
One limitation is that the calibration collapse observed in RLVR training may be rooted in the reward design, which prioritizes final outcomes over intermediate reasoning. The authors suggest that multi-perspective reward designs, like the PPL bonus, can help guide the RLVR process more effectively. They also point to the connection between calibration collapse and LLM hallucination as a promising direction for future work.
That's a fascinating connection. Improving calibration could help reduce hallucinations in LLMs, which is a major challenge in the field. Do the authors discuss any related work in this area?
Yes, the paper provides a comprehensive review of related work, including RL for LLM reasoning, efficient exploration strategies, and recent advances in calibration techniques. They position CDE as a principled and lightweight alternative to more complex exploration methods.
That's great. Before we wrap up, can you summarize the main contributions of the paper?
Certainly. The main contributions are, first, the introduction of the CDE framework, which uses actor and critic curiosity signals to guide exploration in RL for LLMs. Second, theoretical analysis showing that these signals promote diversity and penalize overconfident errors. Third, empirical results demonstrating consistent improvements over strong baselines on challenging reasoning benchmarks. And finally, insights into calibration collapse and its mitigation through curiosity-driven exploration.
That's a comprehensive summary. It's clear that CDE represents a significant step forward in efficient and effective RL training for large language models. Do you have any final thoughts or takeaways?
My main takeaway is that leveraging intrinsic curiosity, both from the actor and the critic, can lead to more robust and calibrated LLMs. The approach is both theoretically grounded and practically effective, making it a valuable addition to the RL toolkit for LLMs.
I agree. It's exciting to see how ideas from cognitive science, like curiosity-driven learning, are being applied to advance artificial intelligence. I'm looking forward to seeing how this line of research develops in the future.
Me too. That brings us to the end of our review. Thank you for joining us on this deep dive into curiosity-driven exploration for efficient reinforcement learning in large language models.
Thank you, everyone. To summarize, today we explored how the CDE framework leverages intrinsic curiosity signals from both the actor and the critic to guide exploration in RL for LLMs, resulting in improved reasoning performance, better calibration, and more robust training dynamics. Stay curious and see you next time.